Next we want to look at multiplication and division with complex numbers that are written in trigonometric form. So I've written over here on the board, suppose the complex number z1 is r1 cosine theta 1 plus I sine theta 1, and z2 is r sub 2 cosine theta sub 2 plus I sine theta sub 2. Then the product of z1 and z2 is the product of r1 and r2 times cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So to multiply two complex numbers that are in trigonometric form, simply multiply their absolute values or the modulus, multiply them each together, and add the angles. So you multiply the numbers in front and add the angles. So therefore you would imagine division would work in just the reverse direction, and it does. z1 divided by z2 is r1 divided by r2 cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So the derivation of these formulas right here is in the book. You can look at them if you want. What's important right here is that we be able to use them. So let's go to the board now and look at our first multiplication problem. Suppose I have just these two complex numbers in trigonometric form. 7 cosine 110 plus I sine 110 times 8 cosine 47 plus I sine 47. By our theorem we have this. The product is going to be 7 times 8 times cosine of 110 degrees plus 47 degrees plus I sine 110 degrees plus 47 degrees. Now I'm just showing that step here so you can see how we apply the formula in actual practice. You probably just multiply and then add these things together right here. So what do we get? 7 times 8 is 56 times cosine of 157 degrees plus I times the sine of 157 degrees. Cosine 157 plus I sine 157, that's the product of those two complex numbers in trigonometric form. Now that's a pretty easy process for multiplication. We simply multiply their absolute values and we add the angles. Let's look at our next problem. Two complex numbers written in algebraic form, z1 and z2. Now I want to multiply z1 times z2, so let's do that. z1 times z2 algebraically is going to be 1 plus I times 4I. Now this is a pretty easy problem with complex numbers written in algebraic form. I'll just use the distributive property. That'll be 4I, whoops, and then I'll multiply here 4 times I squared, which is negative 4. So I get negative 4 plus 4I if I multiply these two complex numbers algebraically, leaving them in standard form like this. Now, what if I want to write them, though, in trigonometric form and see what they look like? Let's first of all draw here a little coordinate system, xy coordinate system. This complex number, 1 plus I, is going to go from the origin out to the point 1, 1. So I know that that's going to be 1 and 1. Its length will be square root 2, and that angle right there will be 45 degrees. So that first complex number, 1 plus I, when I write it in trigonometric form, is square root 2 cosine 45 plus I sine 45. Now how about my second complex number that I have, 4I? Draw a little coordinate system in here. 4I is going to go from the point 0, 0 out to the point x equals 0, y equals 4. So that's this point right here. That will be a vector that will be exactly 4 units long, and it will be 90 degrees up from the positive x-axis. So 4I in trigonometric form will be 4 times cosine 90 plus I times the sine of 90. Now when I want to multiply 1 plus I times 4I, when the complex numbers are written in trigonometric form, I'll multiply their lengths or absolute values and get 4 square root 2, and then I'll add the angles. 90 plus 45 is 135. So I do that. Now that's 4 square root 2 times cosine of 135, negative 1 over square root 2, plus I sine of 135 is 1 over square root 2. I multiply 4 square root 2 times negative 1 over square root 2. I end up with negative 4. That's that product. 4 square root 2 times I times 1 over square root 2 will be 4I. So you can see this offers justification for our rule. I get 4 plus 4I when I multiply the two complex numbers in trigonometric form, and that matches what I got when I multiplied them in algebraic form. Now, some complex numbers are easier to multiply when they're in algebraic form, and some complex numbers will be easier to multiply in trigonometric form. If you know both kinds of multiplication, the choice will be up to you. But there is one part of multiplication in which a trigonometric form really is a lot easier, and that's with raising to powers. Let's look at our next problem. Negative square root 3 plus I raised to the fourth power. Well, I want to take this and raise it to the fourth power. If I was going to do this algebraically, that would mean I would have to write negative square root 3 plus I times negative square root 3 plus I times it again times it again. Now, algebraically, that might take me a while to do that. If I can write my complex number in trigonometric form, then raising it to the nth power is simply a matter of taking its length to the nth power, cosine of n times theta plus I sine of n times theta. The formula right here works for any integer power of this complex number right here. So it's a real nice simple formula to use. So in order to use this formula on this complex number, I have to write it in trigonometric form. So let's take a look. A is equal to negative square root 3. B is equal to 1. That means that R is equal to square root of A squared plus B squared, square root 4, which is 2. So now cosine of theta is equal to negative square root 3 over 2, and the sine of theta is equal to 1/2. So putting these two things together, sine theta is 1/2, cosine theta square root 3 over 2, I know my reference angle is 30 degrees. Cosine is negative and sine is positive. That puts theta into quadrant number 2. So these two things together imply that theta must be 135 degrees. So my complex number in trigonometric form, negative square root 3 plus I to the fourth, is going to be 2 cosine 135 plus I sine 135, all raised to the fourth power. Applying my formula then, what I end up with is, did I say 135? Let's back up for a second. The reference angle is 30 degrees. The angle is in quadrant 2, not 135, is it? It's 150 degrees. So let me change this right here. 150 degrees for theta, so that's going to change this to 150 degrees, and this to 150 degrees. Now, 2 cosine 150 plus I sine 150 all to the fourth. By my formula, that's 2 to the fourth times cosine of 4 times 150 plus I sine of 4 times 150. So you can see this is a real easy process here. 2 to the fourth is 16. 4 times 150, well, that's 4 times 150. 4 times 5 is 20. 4, 5, 6. So cosine of 600 degrees plus I sine 600 degrees. Now, 600 degrees is more than once around, more than one complete revolution, so I'm going to take 360 and subtract it from 600 to get an angle that's coterminal with it, that's between 0 and 360 degrees. So that gives me 16 cosine of, well, let's see, 600 minus 360 should be 240 degrees, plus I sine 240 degrees. Okay, cosine of 240 is going to be what? So that, well, in any case, this is my answer right here in trigonometric form. But now my original problem was given to me in algebraic form, so I want to take my trigonometric form and rewrite it in algebraic form. So let's just evaluate cosine 240 and sine 240 and see what we get here. Cosine 240 is going to be negative 1/2. Plus I times sine of 240 is going to be negative square root 3 over 2. So let's say I multiply 16 times negative 1/2, I get negative 8. And then 16 times negative square root 3 over 2 will be, negative 8I square root 3. And I think I might have said square root 2 and that's square root 3. In any case, 16 times negative 1/2, negative 8. 16 times I times negative square root 3 over 2 is negative 8I square root 3. So here's my answer, in fact, in algebraic form. So I have a complex number here in algebraic form to the 4th power. I decide I don't want to do that. It might be too much work to multiply that times itself 4 times. So I rewrite it in trigonometric form to the 4th power. Very simple process right here. Here's the answer in trigonometric form, and if I want to change that answer into algebraic form, I can do that also. So my answer 2 different ways right here. The last problem I want to work is a division problem, just to show you how the rule works with division. Let's take a look at it. 18 cosine 51 plus I sine 51, and then 12 cosine 32 plus I sine 32, and looks like I need to write my parentheses in here. Okay, so according to my rule then, this is 18 divided by 12 cosine of 51 degrees minus 32 degrees plus I sine 51 degrees minus 32 degrees. So 18 divided by 12, both of those have a 6 in common, so that's 3/2. Or I can write, let's see, 1.5, and then that's times cosine of 51 minus 32 is going to be 19 degrees, right? 19 plus 32, yeah, 19 degrees. So division with complex numbers in trigonometric form, also a very simple process. I simply divide the lengths of the 2 vectors, or the absolute values of the complex numbers, and then I subtract the angles, with the angle in the denominator being subtracted from the angle in the numerator. So that's a look at multiplication and division with complex numbers written in trigonometric form.